And the last talk of this session is given by the other chairperson of the session, Gil Markovich. It's a keynote talk, and the title is A Simple Wet Chemical Technique to Prepare Ultrathin Metal Nanowire Thin Films. And of course, it's given by Tel-Aviv University.
Okay, thank you, Shai. First of all, I would like to thank the organizers, Ilan and Noam, for inviting me to this very pleasant and interesting conference. So I will be telling you about one of the projects in our lab that is about the production, a new process or maybe even new chemistry to produce metal nanowire thin films that are conductive and transparent and may be used for various applications. So this project is done by Daniel Azulay, Tanya Belenkova, Hagit Gilon. It was initiated at the PhD work of Olga Krichevsky that already left us a few years ago. And just in general, an overview of the activities of our group. We basically work on various types of colloidal nanomaterials prepared by colloidal chemistry, with actually a new exception of making materials also by flame pyrolysis. And we focus on various interesting physical properties of small things, either magnetic, ferroelectric, chirality, many different aspects. And, well, I have also advertisements for some posters. Actually, I didn't realize that this poster will be already gone when I speak, but still work by Daniel Schwarzman from our group on nanoscale ferroelectricity using electron holography done in a TEM, which discovered interesting size effects in this property. But unfortunately, this poster is already gone. Another poster that will be now posted in the coming poster session, and I strongly recommend your attention to this poster, is by Ben Maoz on colloidal magnesium oxide nanocrystals and nanosheets with very interesting dielectric and magnetic properties. Okay, but to the subject of today. So as I told you, I'll be telling you about a new way to prepare metal nanowire films. And the idea here is that the nanowires are formed directly on the substrate, not pre-prepared and then spread on the substrate like is being done, for example, on many types of other materials like carbon nanotubes or semiconductor nanowires. And all this is done by simple wet chemistry. It's basically a self-assembly process. And this work is actually now on the current issue of nanolaters. So the introduction actually to this story starts with a different material, which is a close relative of what I will be telling you about. And this is the invention or discovery of mesoporous materials in 1992. These materials are hybrids of inorganic and organic components. They used surfactants, organic surfactant molecules, to form liquid crystalline phases, where the inorganic component was part of this matrix. And when they burnt this organic material, those people were left with very nice ceramic materials with very uniform nanostructures, porous structures, and this was a very interesting development that was followed by a lot of research and so on, although I'm not sure about how many applications resulted of this work. So the idea in this work of mesoporous materials was to start with a dilute solution of a cationic surfactant called CTAB, and it's actually the same surfactant that we are using, complexing it to various anionic species like silicate or other species to form the oxides. and then drying a thin film of this material, going through the phase diagram from micellar solutions through elongated micelles and then to the really liquid crystalline phases like hexagonal or lamellar phases with the drying of the solvent, which is usually a mixture of water and ethanol, and it has to be done, of course, at a certain temperature to avoid crystallization out of the material. And this is how these things were made. Now I'll leave this part of the introduction and get to the point of our work. So the original vision to make metal nanowires was something like that, to be able to make order structures of nanowire arrays, maybe even in a few layers to form some infrastructure for future nanoelectronic circuits. So the direction here was to try to use just simple self-assembly based techniques, the chemist way of dipping substrates in solutions and letting things happen for you. So that was the idea. And what we had at that time, it was 2001 or so, there were some initial publications on ways to make elongated gold nanostructures in solutions. By that time, it was short nanorods that had a certain crystal structure, and again, it was the same surfactant that this time did not template the way it worked in the mesoporous materials, but it did have an effect of adsorbing to different faces of the gold in a different way, and this way to allowing nanorods to grow in solution. And so our idea was to combine the two things that I was talking about. One thing was the mesoporous materials concept, and the other one was the growth of these metal nanorods, which involves also the chemical reduction of metal ions to form the metal particles. So we wanted to combine the two ideas and to go from the micellar solution of, let's say, small gold nano objects toward the organized phases of like hexagonal or maybe even inverse hexagonal phase, and to obtain some uniform metal nanostructures this way. And the initial results, this is already a few years old, by Olga, indeed we were able to obtain, maybe even not at a high yield, but still obtain something like that. And it worked this way. I mean, when we combine the special composition of surfactant, metal ions, and reducing agent, and add it in bulk solution, we get only this standard spherical or other more symmetric shapes of particles. But when we deposited a thin layer a thin film of this solution on a substrate and let the metal reduction occur as the film is drying, we were able to get this very ultra-thin gold and silver nanowires. And we had to use both gold and silver for reasons that actually we still do not fully understand. And got these metal nanowires. And we thought that indeed we are getting something that is happening, the metal growth is happening in a templated way on the surface of the substrate. In this case, it was just carbon substrates used for transmission electron microscopy. And then we went on to try to understand what's the mechanism of formation of these wires. And one of the interesting experiments we could do is cryo-transmission electron microscopy, that is freezing the metal solution as it was drying and the metal is being reduced, stopping the process at different stages to try to understand what's going on. And indeed, as expected, we saw that we start with standard spherical micelles, and then as the film becomes more concentrated, and you see it goes over many minutes, the more elongated micelles are forming, and then after a while you start observing short segments of metal appearing in this structure, which eventually, after complete drying, forms a mesoporous-like structure. And so that was one indication that indeed something, let's say, close to this idea of going through the phase diagram is occurring. And we could also follow the same drying process of the films using polarized optical microscopy, and indeed confirm that towards the end of the drying, we are getting liquid crystal type phases that, rotate the polarization of light and look somewhat similar to hexagonal or similar liquid crystalline phases. Of course, one has to realize that those phase diagrams that I've shown you are only tentative, and probably in reality also due to the high metal concentrations and metal nanostructures forming during the formation of the mesostructures, probably the phase diagram is different and maybe more complex, and this is just, a very rough indication. If you do the process at too low temperature, you get just crystallization of the surfactant without getting the mesostructures. And high-resolution transmission electron microscopy revealed that those nanowires, this is a relatively thick one, usually they are thinner, of the order of 2 or 3 nanometers. They are highly polycrystalline, although we recently discovered that also changing the conditions of formation will make them slightly more crystalline and increase the size of the segments of crystallites that form the wires. But still they are highly polycrystalline. Silver distribution within the wires is of the order of 20 or even less percent to even up to 30%. And also using with Ronit Popovich at the Weizmann Institute, she helped us doing energy filtered TEM. We were able to see that the silver is more or less evenly spread throughout the wires. It's basically an alloy of silver and gold. So a little bit about the chemistry. I'm sorry for this a little bit complex chemistry slide. So we use both gold and silver precursors. Both of them form complexes with the cationic surfactant. And the reducing agent, which is ascorbate, basically, is a mild reducing agent that is not able to fully reduce either the gold or the silver to the metallic state. It can only partially reduce the gold 3+ ions to +1. And then, so this is basically the starting solution, which can be stored on the shelf in the dark for a while. And then when you want to start the process, you have to trigger the reduction of the metal. This is done by various ways. Here I describe one of them, which we found pretty successful, which is adding a very, very small amount of sodium borohydride, which is a strong reducing agent, and is able to reduce a small part of the metal ions in the solution to some initial seeds. We believe that those seeds, precipitating together with the surfactant on the substrate, are initiating the reduction of the metal together with the construction of this mesoporous material. And then a catalytic reduction of the rest of the metal over these initial seeds can progress using the ascorbate now as a reductant. And silver itself can reduce gold. Basically, gold can replace silver in the growing particles. So this is part of the reason why silver, in spite of using in a quantity that is even larger than that of the gold, eventually is at lower concentration in the wires. And this is something that is more typical to what we now have in our process. We get films that are macroscopic in size, basically. This is, again, done on a TEM substrate. The wires, as you can see, are composed of bundles, where in each bundle the wires are quite well oriented and have characteristic size and inter-wire characteristic separation, which resembles the structures of the mesoporous materials, but here the level of order is a shorter range. And we can now do it on many different substrates, silica and silicone and plastics of different polymers of sheets of different kinds. You can see that if we use very low precursor concentration, like on the left-hand picture, then we have to dry a thick solution film, and the nanowire film is not that uniform. But if we use relatively high surfactant concentration, we can now spread thinner films over the substrates, and by this get fairly uniform nanowire films. Looking closely at such nanowire bundles, in this case there are several layers of such nanowire bundles, one on top of the other, on the other in this picture, we can see that now typically the bundle will contain wires of thickness of only 2 to 2.5 nanometers. They are very, very thin and very, very long, and the interwire separation is of the same order. The interwire separation is shorter than the size of a CETA bilayer, which is 3.9 nanometers, and so we still do not fully understand what exactly is the structure of the surfactant around these wires. If you use too low concentrations of silver, then you don't get continuous wires, and this is something that we still need to understand. And what we know from the mesoporous work, this is, for example, one of the important work done on understanding mesoporous material formation at UCLA, you can see that the ordered structures are usually induced by the presence of the interface of the solution with the substrate, and that the bulk of the film is actually quite disordered. We believe that in our case it's the same, and that the nanowires naturally form only at the interface with the substrate and not in the bulk of the film. And then we could go and study the properties of these films. One of the major application that we foresee for these films, and we are now pushing it forward, is the idea of having highly transparent and highly conductive nanowire films. And we were fortunate to find that, for example, when we take a pre-patterned substrate with electrodes and form the film on top of that, the contact of the wires to the electrode is very, very good. It's actually ohmic down to few Kelvin temperatures. And this is, again, probably because the wires originally form at the interface of the substrate and the solution film. And we measured those on the conductivity over several length scales, also using a specialized probe station. It's called the Zyvex system, together with the Ava Barkai in our materials center. It's a probe system situated inside the scanning electron microscope that we can, while viewing the nanowires, not individual nanowires, which are too thin and too small to image, but the whole bundles, we can approach probes and measure the transport properties of the wires. So in all those measurements, we get roughly that the wires have roughly a gold-like resistivity. And now, in terms of sheet resistance, I would say that in general, the sheet resistances that we obtain are now in a fairly broad range, because of still we make the films using different techniques and different parameters. So they are typically between a few tens of ohms square up to, let's say, 1,000 ohms square. Now, the transparency of the films is, I think, fundamentally very high. We are now getting numbers as high as, I think, 97%. Here you see something more typical that is, let's say, slightly, it's around 90%. We think that what interferes with the transmission is actually not the nanowires themselves, but other spherical, larger spherical particles that are almost always formed together with the wires, and we are now trying to reduce them. But now, as I told you, there are some cases where we have almost pure nanowires, and we get to very high transmissions, very close to 100%. And in addition, I mean, when we put the nanowires on polymer substrates that are flexible, we can bend those substrates and with very negligible changes in conductivity. So those nanowire films are very flexible. So this is kind of summarize the transmission, optical transmission versus sheet resistance. Here there are like some dots that belong to silica or PET, polyethylene terephthalate substrates. Where this white cloud is I think our most recent results that are closer or higher in transmission. So this white cloud is roughly where we are at now. And just to, you know, we are not the only ones working on that. Actually, recently there has been an explosion of work published on this idea of making transparent conducting films as replacement for the standard transparent conductors that are used like ITO or zinc oxide family. Well, there are other groups that have published in the last year some work on preparation of ultra-thin gold nanowires in bulk solution, but there's a long way between forming those nanowires in bulk solution to making thin films that are uniform and highly conducting. There's another work that has already shown that prefabricated silver nanorods that have much lower aspect ratio than our nanowires can be very efficient when combined with polymer photovoltaic cells, and already shown that those...
You have 3 minutes.
Those were comparable to ITO. And I think that also very recently a carbon nanotube-based work by a group in Stanford, Zinan Bao, has shown the best results on carbon nanotube transparent electrodes that were also, I think, comparable to ITO. So just to summarize everything I told you, we have a new type of mesoporous material that provides us with a very uniform metal nanowire network films that is very, very simple to implement and to probably also to translate to, you know, industrial processes of printing or spraying and so on. And it's already comparable, I think, to ITO performance, and we are trying to push it forward. I think the plasmonic properties of these nanowires will be interesting to study, and we will do that soon. Another interesting thing would be closer to the original vision of forming networks for nanoelectronics would be orientational ordering over a longer range of those nanowire bundles, and I think this will be possible too. And I think, well, right now we are trying to forward this idea for printable photovoltaic cells. And I'll thank you for your attention and be happy to hear some questions.
Are there any questions from the audience?
Here. Here on this side there are some. Can interpenetrate. Yeah. Yeah, that's true. I think this is a good point. Yeah, probably they are interpenetrating, and this is the reason for that. And yeah, you're right. And another possibility is to take double-chain surfactants that are less soluble in water, but at low concentrations. Actually, we had some preliminary indications that those even improve the yield of formation of those nanowires. And in that case, probably you will get larger spacing because then you have 2 tails per head. So they cannot so much interpenetrate, maybe.
Well, actually, I wonder whether it is maybe possible to extrapolate to see that maybe
Yeah, true. I mean, sure, we need to do that. Yeah, we need to go to a synchrotron probably. And, yeah.
So I have one question, and that is, to what extent are the properties of the nano dimensions reflected, and how is it related to how are they related to the diameter of the nanowires that you produce?
You mean in terms of physical properties of the wires that might be different from bulk metal? Or... So if I understood the question, it is about what is special about those nanowires in terms of physical properties, maybe? Okay, so yeah, we tried looking at the transport properties of the nanowires because they are so thin, so you would expect that, the mean free path and things like that will be affected. Maybe because they are so polycrystalline, we didn't observe it down, I think, to 2 Kelvin, but it could appear at lower temperature, maybe at sub-degree Kelvin, so it's more difficult to do the experiment. We need some physicists, low-temperature physicists to help us. And in terms of the plasmons, I think nobody did study plasmon in such high aspect ratio nanowires, and we will try also to simulate this, the plasmonic behavior, and try to using a microscope to focus, let's say, on a bundle or something like that, and to take the plasmon spectrum of something like that. But I expect that there you will see something unique or interesting.
All the speakers of the session for standing within the time limitations, and let's have coffee together now.